Welcome in the last section of our Cassandra course, and in this section we'll be using as use cases for near real-time streaming processing using Spark Streaming, and we'll be connecting Spark Streaming with Cassandra, because in Spark Streaming and in streaming world we often need to perform stateful processing of stream, and if we have stream state, then we need to keep that state in some persistent data store. And Cassandra, as this is a key value store, is a perfect fit for it, because we can keep state using partition key that is also a user ID of our users that we are analyzing using real-time streaming. And in this section, we'll be looking at the Spark Streaming architecture, we'll be creating project in Apache Spark Streaming, we'll be defining data source and data sink, and creating stateful stream processing. And in this first video, I'll be using the use cases and when we need to use real-time stream processing. So firstly, we will answer the question, why even use streaming? Then we'll be looking at the Spark Streaming architecture and at the DStream API. So when to use streaming? So we can use streaming if there is a need for processing events in the near real-time fashion. If we need results to be available in seconds, then we need to perform some kind of streaming. And if we need to react very quickly on users' behavior, for example, if you want to employ a fraud detection or anomaly detection. And let's look how Spark Streaming does look like. So Spark Streaming is an application that's subscribed to some streaming data sources like Akka, Kafka, Amazon Kinesis or Flume, or it could also load data from some static data sources like MySQL, Cassandra, MongoDB, Elasticsearch, Parquet, Postgres or HDFS. Then we have an actual streaming processing in the Spark Streaming app, and we can process with Data Frames API, with SQL API, we can use Spark SQL of course, and we can also use machine learning models using MLlib. So we can train models with live data and use that trained model. At the end of some job that process stream, we have some results. So that result could be published to Kafka for further chaining of other stream processing part, or we can save results to Cassandra, Parquet or HDFS for further static access. And Spark Streaming Pros is like it has uniform API with Spark Batch that we used 2 sections ago, and also DStream is a primary abstractions containing multiple RDDs. So RDD is a known API for us now, and we can use it from DStream. So DStream contains a number of RDDs. We have an original DStream, and we can perform some transformations on every RDD. We can perform transformation on first RDD, and we can also perform window-based operations. So we can window more RDD into one window and perform operations on that window. For example, if you want to analyze activity within some session window. And Spark Streaming employs micro batches approach. So data arrive in the batches, and we are configuring the batch duration. All events that arrive within duration are packed into one batch of data. Micro batches works like this. So we have a high frequency input data stream, and Spark Streaming is batching that into smaller batches. Then we have Spark Engine that is doing an actual processing, and then we have result of processed data that is also in micro batches. And when considering micro batches approach, we can set a batch duration, and if the batch duration is longer, we get the higher throughput, but higher latency also. But if the batch duration is smaller, we get lower latency, but also lower throughput. So let's look how does it behave when we compare latency versus throughput. So if we have a batch size of 5 seconds, latency will be at least 5 seconds and throughput will be 1000 elements, let's say. But if we will decrease batch size to 1 second, then latency will be at least 1 second, so it is better for low latency systems, but throughput will be lower. So we will not be able to process so much events in same time period. And Spark Streaming also uses checkpointing for failure recovery. So it saves the actual intermediate RDD data to reliable distributed file system like for example HDFS. and we need to set checkpointing directory if we have a stateful processing. In case of the worker failure, it can resume computing by loading checkpoint data.